So good afternoon to everyone. I welcome all of you to this 54th lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It's a pleasure to introduce Professor Bijan Kumar Bagchi. Professor Bagchi received his BSc, MSc, and PhD degrees from the University of Kolkata. After his PhD, he joined as an associate at the Rai Chaudhary Lab of Presidency College, Kolkata. Subsequently, he went to the Institute for Theoretical Physics, University of Bern, Switzerland, as a visiting scientist. A former professor with the University of Kolkata, he has served as its head of the Department of Physics, I think, and also as the coordinator of the UGC Special Assistance Program. He later became a UGC Emeritus Fellow in the Department of Physics, Shiv Nadar University, where he is currently holding the post of professor. Dr. Bagchi has held several research positions in Europe and the US, professorships at Physics Nuclear Theory at Kung University, Taiwan. During the past few years, his research has focused in developing models for position-dependent mass systems, generating solutions of the Dirac equation using supersymmetric methods, extensive study of parity-time symmetric models, estimating the tunneling of Hawking radiation, analyzing group theoretic approach for rationally extended shape invariant potentials, and so on. He has published about 170 research articles in various international and national journals in the area of theoretical physics, and is the author of 3 books entitled Supersymmetry in Quantum and Classical Mechanics, Advanced Classical Mechanics, and Partial Differential Equations for Mathematical Physicists, all published by the CRC Press UK, respectively in the years 2000, 2017, and 2019. He has served in the various professional bodies like CSIR, UGC, and UPSC committees, and has been an expert of various selection committees in India and abroad, and member of PhD committee and board of studies of various universities. Currently, he is supervising 3 students at Shiv Nadar University. With this short introduction, now I invite Professor Bijan Kumar Bagchi to deliver this lecture. Over to you, Professor.
Thank you, Professor Lakshmanan, for your kind words. And also Professor Sentivalan for inviting me to this lecture series in nonlinear dynamics. I'll talk today on some perspectives of parity-time symmetry in quantum mechanics. Basically, I'll gloss over certain topics and try to convince you about the usefulness of PT symmetric systems in applicable physics. Now, outline of my talk, let me give that. First of all, I'll outline PT symmetry. Then I'll give a background of standard solvable systems. I'll discuss both PT symmetry and pseudo hermiticity, the distinction between the two concepts. I'll give few examples of PT symmetry, and of course, my examples will also include models of pseudo hermiticity. I'll discuss in some detail complexified scarf potential, which is of course PT symmetric. And then I'll move on to the group theoretical Lie algebraic approach and present modified SL2C algebra and how to realize this algebra in the context of non-Hermitian systems. I'll briefly dwell upon wave function treatment, and then finally I'll give you a summary. Now, over the years, non-Hermitian quantum mechanics it has gradually emerged. It is an active field of research with a wide range of applications. As we all know, non-Hermitian Hamiltonians undergo non-unitary evolution, and these Hamiltonians generally describe open systems through gain and loss of particles. In particular, the subclass of non-Hermitian systems that constitute PT symmetry has proved to be an area of continuous attention for the last 20 years. Now, the definition is very simple. It is controlled, PT symmetry is controlled by the joint action of parity and time reversal transformations. You know how parity behaves. X is transposed to minus X, P goes to minus P. For the time reversal operator, X goes to X, P goes to minus P, and these changes make I going to go to minus I, and PT as a whole is joint transformation. That makes X goes to minus X, P goes to P, and I goes to minus I. This idea of PT symmetry was first concretized in a paper of Bender and Boettcher in 1998. Even before 1998, people knew PT symmetry, but no concrete model was proposed. Especially the features of PT symmetry were not known until this paper was published in 1998. The point was to conjecture that the whole class of non-Hermitian Hamiltonians that respect PT symmetry may exhibit under some conditions, some mathematical conditions related to PT being exact, which means the Hamiltonian sharing its eigenstates with the PT operator, or be spontaneously broken, and which means the Hamiltonian not sharing its eigenstates with the PT operator, real or conjugate pairs of eigenvalues, energy eigenvalues. This implies balanced loss and gain in the system. However, it needs to be stressed that PT symmetry is neither necessary nor sufficient for the reality of the spectrum. Specifically, while with respect to the parity operator, gain and loss are interchanged, you can just work out, gain and loss are interchanged. The operator T turns the system with gain into a system with loss and reversely. The time reversal operator T and hence PT is nonlinear. More precisely, it is an antilinear operator. In models of PT symmetry, the fundamental Heisenberg algebra is assumed to remain invariant. Now, this is a crucial assumption. The xp minus pi px remains the same, it is IH cut. A large family of exactly solvable PT symmetric potentials has been discovered during the past 1.5 decades. And interestingly, there have been several applications to nonlinear systems to which this conference is dedicated. Most of such potentials have analogs in the background of solvable potentials in conventional quantum mechanical scenario. Now, background of some standard sort of solvable systems. Exactly solvable systems are of everlasting interest in quantum mechanics. An early attempt to track down a class of solvable potentials is due to Infeld and Hull by proposing what is called the factorization method. Of course, factorization method was known even before Infeld and Hull due to a paper of Schrödinger in 1943. Later, extensive work has been done to improve upon their results. The list of solvable systems includes derivation of normalizable solutions in terms of hypergeometric, Jacobi, confluent hypergeometric, Bessel, or Legendre functions. With the advent of supersymmetric quantum mechanics, the study of solvable potentials has been revived, and in this framework, some new ones also have been discovered. The list of exactly solvable systems further expanded in the context of polynomial Heisenberg algebra, which offer additional degeneracies of the energy levels. In recent times, discovery of exceptional orthogonal polynomials, fondly called EOP, also known as XM Lagoude and XM Jacobi polynomials that start with polynomials of degree 1 or higher, but reducible to tractable forms of differential equations, provided association with the bounds to wave functions of certain solvable potentials. These include the rational extensions of known shape-independent systems such as radial oscillator, generalized Cauchy-Taylor, and scarf potentials. Now, the conventional wisdom, there are 4 fundamental axioms in quantum mechanics that we have learned to live by are the following. The first one is the energy spectrum is required to be real because the measurements are supposed to yield real results. Hence, one assumes the underlying Hamiltonians to be Hermitian. Number 2, the energy spectrum is bounded from below. That is, the system has a stable lowest energy state. Number 3, time evolution is unitary, which means probability conserving, because the expected result of a probability measurement cannot grow or decay in time. And lastly, fourthly, non-Hermitian Hamiltonians have been traditionally employed to describe dissipative processes. They cannot be regarded as fundamental because they violate unitarity. Essence of PT symmetry is that a non-Hermitian Hamiltonian admitting such a symmetry can possess real bound state spectrum and not be spontaneously broken. PT systems are appealing because of the intriguing spectral properties. The standard feature of ordinary quantum mechanics is that observables are represented by operators that are self-adjoint under the standard inner product. But a non-Hermitian PT symmetry Hamiltonian is an open quantum system where loss of unitarity is not a fundamental problem. On face, even without it, its description is valid irrespective of whether the spectrum of the Hamiltonian is purely real or has compressed conjugate pairs eigenvalues. Now, let me just point out as to what we mean by Hermiticity. Now, Hermiticity implies, remember, Hermiticity is a sufficient condition only. Hermiticity implies real spectrum. How it goes about? H on psi is E psi, as we all know. Now, you sandwich H between the state psi, and that will be E psi psi. The left-hand side is real, right-hand side is real and positive, and hence E is real. In terms of wave function, all this can be translated to E minus E star times psi star psi dx equal to 0. But psi star psi dx is positive definite, hence E equal to E star, implying E is real. What about PT symmetry? Unbroken or exact PT implies real eigenvalues. You can see there this unbroken PT, which means the Hamiltonian, the PT operator commutes with the Hamiltonian, the first one, and the eigenfunction is an eigenfunction of the PT operator, which is PT phi equal to phi. Now you can work out the steps. If epsilon is the energy, epsilon phi is H phi, and you can, from the first equation, if you can replace it by H PT phi, which is PT H phi, and that is PT of epsilon phi, and epsilon, if it is pulled out, to make it star, then it is epsilon star PT phi, and you can see it is epsilon star phi. So if you compare the two sides, it is real. Now, spontaneously broken PT gives conjugate eigenvalues. This can be seen easily. This HPT commutator is 0, which means PT and H are compatible. And then you assume that PT phi is not equal to phi, as you had in the case of the unbroken symmetry. Suppose PT phi is not equal to phi, and then more explicitly, H phi 1 is epsilon 1 phi 1, H phi 2 is epsilon 2 phi 2, and PT phi 1 is not equal to phi 1, but let's call it phi 2. And then you can work out PT H phi 1 is PT epsilon 1 phi 1 from one of the equations just stated. And these imply HPT phi 1 equal to epsilon 1 star PT phi 1, which is epsilon, it's epsilon 1 star phi, and hence H phi 2 is equal to epsilon 1 star phi 2. Now, what is pseudo-Hermiticity? PT symmetry has roots in the theory of pseudo-Hermitian operators. Note that every Hamiltonian with a real spectrum is pseudo-Hermitian. H is pseudo-Hermitian if there exists a Hermitian and invertible operator eta acting in a Krein space. This is a technical terminology. I'm not going to discuss this in detail here. So acting in a Krein space satisfying H dagger equal to eta H eta inverse. Now it's interesting to compare this with the Dyson equation. Eta is a Dyson mark and is given by the equation H equal to eta H eta inverse Small h is Hermitian, whereas capital H is non-Hermitian. So you can just compare the two. Now, let me put it this way, that this kind of pseudo-Hermiticity, it was known to physicists in the early 40s, Pauli, Dirac, and later L.K. Pandit of TIFR in 1960s. They also worked in this kind of theory of pseudo-Hermitian theories. But those papers have been forgotten now. The class of PT-symmetric Hamiltonians, let's call it H equal to minus d2 dx square, controlled by the potential Vx. And this potential is assumed to be PT-symmetric, which means Vx equal to V star of minus x is P pseudo-Hermitian. This can be checked very easily. But note that P pseudo-Hermiticity and PT-symmetry are distinct properties. For the momentum-dependent non-Hermitian Hamiltonians, it is not really physical, but for an application point of view, this is interesting. The first one, H1 is P square plus x square P, and H2 is P square plus I times x square P plus Px square. You can check that H1 is PT-symmetry, but not P pseudo-Hermitian, while H2 is P pseudo-Hermitian, not PT-symmetry. Only pseudo-Hermiticity serves as a necessary condition. So you can see that pseudo-Hermiticity is not necessary and sufficient. Pseudo-Hermiticity serves as a necessary condition for the reality of the spectrum. A condition that is both necessary and sufficient is coupling the pseudo-Hermiticity with the existence of a positive definite metric eta plus in the manner that you can factorize it like O dagger rho. Eta acts as an indefinite metric in a Klein space so that H itself is self-adjoint in such a Klein space. In the early days, when Mustafa Zadeh wrote his pioneering papers, 3 papers together in Journal of Mathematical Physics, volume 43. So in his days, spectral analysis was proposed only for the class of positive definite metric eta plus. But for the general case, Goenther and others, they have come out with some certain theories. Okay. The window of the positive definite inner product on H in which H is acting may be defined. This script H is the Hilbert space in which the Hamiltonian H is acting may be defined in terms of the overlap as what I have shown there. This eta plus is pushed in. The Hilbert space is equipped with the Hilbert space equipped with the above inner product is identified as the physical Hilbert space H phase. The pseudo-Hermiticity of the Hamiltonian is given by the formula where I have written explicitly eta as eta plus. Any observable which belongs to the physical Hilbert space is related to the Hermitian operator by means of a symmetry transformator, where rho is square root of eta plus is unitary and maps H phase to H. Now, this is also known to people working in differential equations. You have a differential operator, a second order differential operator. In general, if that second order differential operator, if it is only d2 dx square plus some function of x, then this is of course Hermitian. But if we put in the ddx, it becomes non-Hermitian. So this kind of thing is going on here. So make a sort of transformation going from the Hermitian to non-Hermitian operator, and the certain properties are to be satisfied. I'm not going to those properties in detail, but this is called similarity transformation. Now, I come to a few examples of PT potentials. Number one, Bender Boettcher's imaginary cubic potential. This has become very famous. This is non-Hermitian but PT symmetric. IG x's cube, that I changes sign, and x's cube also changes sign, so the whole thing remains invariant. And he worked out that all energy eigenvalues are real and positive. Generalizable to the parametric PT symmetric form, we write it as x squared times ix to the epsilon. The entire class of H reveals an interesting aspect, and this is the type of figure. If you plot the energy in terms of epsilon, you get this kind of figure. The point is that numerically one finds that for all positive definite, positive semi-definite epsilon, all the eigenvalues are entirely real and positive. For epsilon smaller than 0, there are only complex eigenvalues. And epsilon equal to 0 speaks of the point of phase transition that coincides with the harmonic oscillator whose energy levels under certain notational convenience is given by En equal to twice n plus 1. In particular, for epsilon between -1 and 0, there are a finite number of real positive eigenvalues and an infinite number of conjugate complex pairs of eigenvalues. We say that when epsilon is greater than or equal to 0, the PT symmetry is unbroken, but when epsilon is smaller than 0, PT symmetry is broken. So this generated a lot of academic interest. The second one, this PT symmetric square well potential. You can see I've given the intervals -1, x between -1 and 0, and x between 0 and +1. The potentials are defined as left side L is IZ, psi L -1 is 0, and the right side is V R x equal to -IZ, psi R equal to psi R +1 equal to 0. This Z is a coupling strength, and when Z goes to 0, it depicts the real square well. Eigenfunctions at the endpoints of the intervals are enforced to be vanishing, as is the case with the real square well problem with impenetrable walls. Now, these eigenfunctions have some complicated forms, and the main thing is that kn square, which is appearing there in the argument, is given by it's complex. It's given by -E and -IZ, and that can be written as Sn minus Itn whole square. Now I can solve them, and those are the expressions for Tn and Sn. Acceptable solutions have to satisfy the Dirichlet's conditions and the continuity conditions at the origin. So the conclusion is that as long as Z stays below critical value, called ZC, eigenvalues are real and PT symmetry holds for the eigenfunctions. However, above this threshold, Z greater than ZC, the picture changes dramatically and one runs into pairs of compressed conjugate eigenvalues. So this is also a toy model, and that really works for the case of PT symmetry. So the second one means the PT is broken when the corresponding eigenfunction cease to remain PT symmetry. The supersymmetric condition is given by the forms -IZ plus some cosec hyperbole square additions, and these are very tightly defined in the sense that one can have just a minute. It means that they can be generated from the superpotentials, one for the right and one for the left. The boundary conditions are in eigenfunctions are specified as given there, and the unbroken phase is Z less than ZC, and where you have the reduction to the standard sec square type in the Z going to 0 limit, while for Z greater than ZC, both PT breaking and partially restored PT phases appear. Third example is a competing PT potentials. We have a short range potential, a combination of delta functions, and you can see that the plus Iz rather, it is a localized gain, and minus Iz is a localized loss at meter symmetric position equal to plus minus A. Z is assumed to be positive. Broad and constant PT potentials, and this depicts a constant gain potential for x greater than 0 with meter symmetric loss region for x less than 0. So this was artificially created, this potential, but it works. It is very interesting in that sense that it has all the features of the PT symmetry, and its phase transition to the region where it's broken. When z equal to 0, the threshold potential strength is done numerically. It is 4.48, while for z equal to 0 and a equal to L by 2, it is z equal to 5. In the two cases, eigenvalues are real. For that interval z between minus zc and zc, and xi between minus xc and xc. When both of them are non-zero in xi, PT symmetric phase plane, the ranges can be characterized according to what has been stated, according to z being xi as a sandwich between zc minus xi and zc plus xi. Xi is taken to be positive. Now, there is an interesting case of a non-PT symmetric potentials. Sometimes non-PT symmetric potentials can exhibit features of a PT symmetric spectral behavior. Consider a pseudo-Hermitian-like constraint, eta L equal to L dagger eta. That is the intertwining relation, some kind of an intertwining relation. This L is given by this operator delta 2 plus Vx. Vx is taken to be complex. And we choose a P-induced eta in the form that eta is defined by P, the parity operator, operating on delta 2 plus AX delta plus BX. Now, you can work out those results which I've given in terms of Vx and the constraints on A and B. So these are the diagrams. You can see 4 diagrams, the profile of the base potential V0 and the profile of the partnered V. There are 2. If we apply supersymmetry, you will have the base potential V0 and you can have the partnered V. The spectrum of V0 is given in C, that you can see it is entirely real, but spectrum of V displayed in figure D, you can see that complex pair of complex eigenvalues emerges, signaling occurrence of a phase transition. Now I turn to the complexified offset, which is studied quite in detail by several authors in this area of PT symmetry. It's called CSP, complexified scarf potential. That is the standard form. The coupling parameters are subject to A being positive and B greater than half. The interesting features CSP was identified in the early days of PT symmetry using complexified supersymmetric approach, and it was proved that it is isospectral to Sekar-Cooley square potential with real spectra. This potential, we found that it is amenable to SL2C algebra treatment. A unique property is the existence of 2 series of energy levels, and this is very unique for this kind of potential. It doesn't exist for other potentials. At least we have not found so far. So this existence of 2 series of energy levels, special for scarf 2, and associated with 2 non-commuting complex D algebras. And here we have the existence of a spectral singularity. Perhaps you know spectral singularity. There is a crucial difference between the exceptional point and spectral singularity. Exceptional points are particular states in the discrete spectrum of the operator, where 2 eigenvalues of different energies coalesce to form a unique state. Now, spectral singularity, this has a nature similar to exceptional points, but within the continuous spectrum of a non-Hermitian operator. Now, this CSP or complexified scarf potential, this admits of a rational extension. You can see there, those are the extra terms, and one can work out, evaluate the eigenfunctions, and these are expressed in terms of x1 exceptional orthogonal polynomials of Jacobi type, decomplicated. Now there is a second rational extension, the parametric transformation B going to A plus half and the other way around in the CSP, that symmetry complexified scalar potential enjoys, and this leads to, because of this symmetry, we have a new rationally extended PT symmetry scarf 2 potential. This is given by VAB R1, and the wave functions have also been evaluated in terms of EOPJ. The new rationally extended potential also generalized to the potentials whose solutions are in terms of XM exceptional Jacobi polynomials given by rather a complicated form, and wave functions too are they don't have a very interesting appearance. But this potential is isospectral to the conventional one. Invariance of the transmission and reflection amplitudes, invariant under the transformation B going to A plus up and vice versa, as can be seen from the expression of TK, transmission coefficient, and we also have the reflection coefficient. So that symmetry can be easily checked. The poles of the gamma functions give rise to the exact bound state energy spectrums. Now I spend a few words on the Lie algebraic approach. You can see the algebra. There are different realizations of the generators which are given there. And if you substitute those realizations in the commutators, we will run into constraints for f and g. Constraints for f and g are quite simple. As you can see, f prime equal to 1 minus f square. F prime is the derivative with respect to the special coordinate, and g prime equal to minus fg. There also the prime is the derivative with respect to this with the spatial coordinate. Now the point is that there can be only 3 classes of solutions. Not many really, only 3 classes. Those are given the combination tan hyperbolic, sec hyperbolic, cot hyperbolic, cosec hyperbolic, and of course for the most it is plus minus 1 e to the plus minus 6. Now you can work out the Casimir operator and write down the irreducible representation. The Schrodinger equation for the J square has that form, and this defines a family of potentials given by Vm. The irreducible representation of SL2C thus correspond to a given eigenvalue to various potentials. So this is the spirit of the potential algebra. Again, the energy eigenvalues, the M is complex, so we write it as mr plus I mi minus n minus half whole square. Real eigenvalues therefore correspond to mi equal to 0, and complex eigenvalues correspond to a mi not equal to 0. Wave functions from, you can work out that, the first order equation it is, J minus form you have. So you can compute the wave functions with the regularity condition MR going is greater than half and B are positive. And then you can generate 3 different classes of complex potential. This we did extensively for the scarf. So we have the special properties. Complexified scarf is both PT symmetric and P pseudo Hermitian. Complexified Poisson-Taylor is PT symmetric and P pseudo Hermitian, but complex modes is non-PT but pseudo Hermitian under imaginary shift of the coordinate. Now this is very interesting. Complex mode is non-PT, yet it admits of real eigenvalues because it is pseudo Hermitian under imaginary shift of the coordinate. And there is some interplay of the parameters. The calculations are long and quite tedious, and you run into 2 series of real eigenvalues. Their forms are given, and also the regularity condition fixes the values of n. This general form was first proposed by Zafar Ahmed in 2001. So the 2 cases are discussed, and the parameterizations we have done to make a connection between our scheme and Zafar Ahmed's scheme. We have identified V1 equal to B squared plus A times A plus 1 and V2 equal to minus B times 2A plus 1, and we have that design. Now we come to a modified version of SL2 algebra, SL2C data, SL2C algebra, and how to realize this algebra. So these are the steps. I did not go through the details. This was done in a collaborative work with Yadav, Avinash Khare, Nisha Kumari, and Bhavani Mandal. The new generators in this modified scheme, we worked out the generators and they satisfy SL2C algebra, but you have to have the restrictions that is given by equation number 2. This restriction is somewhat different from the one we got previously. You can see that previously we got it slightly different. The Casimir operator is worked out for the bound states. The basis is characterized by the 2 equations, and the differential realization of the Casimir J2 is given by the form, rather a longish one. The expression is the right side. The basis in terms of the wave expansion is defined there, and this ijk satisfies the Schrodinger equation, and Vkx is the 1-parameter family of the k-dependent potentials. The corresponding energy eigenvalues are simple, minus j plus half whole square. By replacing ux k plus minus half by ux m k plus minus half, the above realizations are also suitable for the 1-parameter family of rationally extended shape-independent potential associated with the xm exceptional orthogonal potentials. For a cake, if you put m equal to 0, that is ux 0k minus half equal to 0, we get the expressions for the corresponding conventional potentials. Thus, the Hamiltonian in terms of the Casimir operator of SL2C is given by h equal to minus j square plus 1/4. So here we are concerned with the unitary representation corresponding to the discrete principal series Bj plus, for which j is less than 0, and this is given by k equal to minus j plus n, and the energy eigenvalues correspond to En equal to minus n minus k minus half whole square, whole thing whole square. So these are the representations for fx and dx, and naturally we have an expression for u for the extended complex scarf-2 potential. On putting all these functions f and g, we get the expression for new rationally extended PT symmetric potentials with the parameter b being replaced by k. So these are the new rationally extended compressed potentials, SCARF2 potentials having same energy eigenvalues and associated with the typical XM exceptional orthogonal polynomials, and those are the expressions. Now I just point out this wave function treatment. We focus on this general form. You can see there Vx is given by minus V1. That's a generalized SCARF potential, and we take a formal solution as given by the product seen there, and the four constants by substituting the four constants lambda, mu, alpha, beta can be determined, and this is the transform Schrodinger equation. And you can see the asymptotic behavior of the wave function is controlled by the factor. There is a factor. So this implies for a decent behavior, decent asymptotic behavior, real part of lambda must be greater than a positive. And that is the compatibility conditions. We adopt the notations P, Q, and S in terms of V1 and V2. And these are the results. It doesn't make much sense here, but then, of course, this has some important role to play in tracking down the spectral singularity of this in the system, hiding in the system. So those are the expressions for the compressed conjugate energy, and that's the simple result. Both cases, bound state wave functions are given by that form. Combination of sec hyperbolic square and exponential of some argument and p and alpha beta y. And this is a spectral singularity I was talking about. This is for the case, the first one, modulus of Vt greater than V1 plus 1/4. And you can see the energy eigenvalues appear in the form. Now, if you set p minus half equal to n, then you can see that if you put p n minus half equal to n, let's have a close look. If you put p minus half equal to n, then this whole thing cancels, and I square becomes minus 1, and you don't have really complex conjugate eigenvalues now. They collapse into a single real and positive value. And that is C constant, it is subjective. These are the wave functions, and that is the asymptotic behavior. And the solutions are such that the size, the typical behavior, there is that those solutions are both proportional to psi n minus x, and they are linearly dependent. We therefore conclude that E star is a spectral singularity of H. Normally, in PT spontaneously broken scenarios, compressed conjugate eigenvalues develop, and the energy eigenfunction cease to be eigenstates of the PT operator while the pseudonorm vanishes. I have not discussed pseudonorm here, but maybe I can just focus on a few slides on this. In the present case, we have an exceptional situation. The potential is PT symmetric, but its wave functions are not so. Yet, the corresponding eigenvalues, eigenvalue E star is real and positive, and this signals what is called the spectral spectral singularity hiding in the system. So you can work out the pseudo norm. So left hand side represents the expression for the pseudo norm, and then the question now becomes interesting as to what happens to the pseudo norm after collapse. So after the collapse of En plus and En minus, the pseudo norm of the wave functions assumes a finite non-vanishing value. Now I move on to the summary. Research in the PT symmetric compressed potentials has actively flourished in the past decade and a half. We focused on the CSP, whose study is important, especially in connection with solitonic resonance. CSP is isospectral to a real potential admitting of a real discrete spectrum. This is within the framework of supersymmetric quantum mechanics. It was realized from the very early days of PT symmetry that in the framework of two non-commuting interconnecting complex cell2 algebras, there exist two series of energy levels associated with it. CSP has been interpreted in terms of supersymmetry and the group theoretic framework of an SL2C algebra. There exists a rationally extended version of complexified SCARF potential whose wave functions are controlled by exceptional orthogonal polynomials. For certain conditions prevailing upon its parameters, CPS runs into a single zero-width resonance or the so-called spectral singularity. Different parametric symmetries for the CSP provide a new set of bound states with new potentials. These are all new results. And we studied the parametric symmetries using the powerful technique of the group theoretic methods, in which the Hamiltonian for the conventional as well as for the rationally extended ones are expressed purely in terms of the modified Casimir operator of the SL2 group. So with this note, I thank the audience for patiently hearing to what I was saying. Now, if you have any questions, I'll be glad to answer. So I stop here.
So thank you very much, Professor Bagchi, for providing a very interesting overview of symmetric complex potentials of different forms. So the audience are the forum is open for questions. The audience can come up with questions. I think Chitika Ruby has raised a hand. So, Chitika, you can ask your questions.
Yes, Chitika, I've been reading your papers. Those are really interesting ones, especially the first one with respect to Professor Lakshmanan and Sentivelan. You opened up a new direction of momentum-dependent mass systems. That was very interesting.
Thank you, sir. Thank you, sir. I met you in Calcutta, sir, at Science College.
Oh, did you? When was it?
I think 2016.
Yeah, I now I remember. Yes, I met you. Yeah.
Yes, sir.
Thank you for pointing out.
Thank you, sir. Thank you for your interesting talk, sir. Sir, actually, I heard a doubt regarding that the more complexified, most potential is non-symmetric, and it shows that pseudo hermiticity as well as along with that under imaginary shift. So does it mean that any translation symmetry has been preserved, sir? Does the system shows any?
Yes, that is a good question. I think that's really a good question. Now, now the problem is that if you make an imaginary shift of the coordinate and then work out the commutator, then something will go wrong. But Zafar Ahmed did something interesting there. He did that as well as he hided it with respect to some other operator, and he got real eigenvalues. He gave some explanations that it is due to this pseudo hermiticity of the system rather than PT. So this is a case where it is not. It is a non-Hermitian system, but admitting real eigenvalues. But I think this point has been probed in detail by Zafar Ahmed in a series of papers. You can look up his papers. Yes, that is an interesting question.
Okay, sir. Thank you, sir.
Yeah, you, sir. There was some question by Charumadi.
Yes.
Charumadi, I think she raised some questions, but I don't see that. Charumadi, are you here?
Yes, sir. Yes, sir.
Yeah,
sir, in slide 17, you can explain about the graphs, the eigenvalue graphs.
Yeah, I'm not getting you clearly, your voice.
Sir, yeah. In your piece, slide 17, sir, the eigenvalue graphs.
Yes, what can you be a little bit loud? What is the question, please?
Sir, in slide 17, can you explain more about the graphs, sir? How the eigenvalues vary from the broken and unbroken symmetry?
Slide number 17.
17, yes.
Yeah, this is the one.
Yes, sir. You can explain how the eigenvalues and goes from the broken to unbroken.
Look, I'm not the person who should explain this. It is Carl Bender's pet figure and pet model. So I summarized his views. He's given there that if epsilon is greater than or equal to 0, you can see from the figure all the eigenvalues are entirely real and positive. This was his fundamental result. But then he worked in more detail and played around with the parameter epsilon, and to his surprise, he saw that when epsilon is negative, there do exist complex eigenvalues. So there was definitely a phase transition at epsilon equal to 0. And the epsilon equal to 0 incidentally coincided with the harmonic oscillator model. So on either side of the harmonic oscillator, on one side, eigenvalues are, if you make a slight change for the harmonic oscillator, just have a look at the model. This is the model. You can see that if epsilon equal to 0, then it looks like p square plus x square. So that is the harmonic oscillator model. Now, if you go a little bit ahead, if you put epsilon greater than or equal to 0, then it deviates slightly from the harmonic oscillator. So there are two ways. One is epsilon greater than or equal to 0, or epsilon strictly negative. And he found that the eigenvalues are entirely real and positive for epsilon greater than or equal to 0. But the system runs into complex eigenvalues for negative values of epsilon. But the additional one, if epsilon lies between -1 and 0, there are, and this is the result he got, that there are a finite number of real positive eigenvalues and infinite number of conjugate complex pairs of eigenvalues. So this is all diagrammatic interpretation. But I don't think it has any physical application as such. But this is for academic. This has an academic interest only.
So in the figure, you are showing only the bound states.
Yes, that's true.
So the complex eigenvalues are not shown here.
No, it's not that, but there are other figures also. I just wanted to point out that this was the first example we started with. The game of parity-symmetry started with.
Thank you, sir. Thank you so much.
Any other questions? Anybody wants to ask any other question? So, Professor Bagchi, can you explain what does this complexified sharp Herschel-Teller-Morse potentials imply? Physically, what do they imply?
Physically, complexified scarf potential, you mean?
Yes.
Yeah, that is also interesting. But the answer to your question is that this complexified scarf, if you treat it supersymmetrically, it has a real partner, and that is related to the solitonic studies, the solitonic potential. So this is very interesting that if you take this one potential and work out
the solitonic potential, you mean secant h square form?
Yeah, but if you take this potential and apply supersymmetric quantum mechanics, we did that. And then interesting, this is one hand of the potential. That supersymmetry, there are the partner potentials. One is, if we fix to be complexified scarf, the other one will necessarily be the sec hyperbolic square. So you can make little changes, but the whole feature remains the same.
Okay. Thank you very much.
But this is interesting. Your question is interesting. I've thought long over it, that how come that this potential which is complex has a real partner. Now, when you worked out when you define the supersymmetry with respect to this particular potential, it came to a surprise that it holds a partner which is entirely real, and it's a typical sec hyperbolic square. We tried to play around with the sec hyperbolic square, but it was a kind of no-go. But this is also, I think, it's an open thing that you can take other solitonic profiles, not necessarily sec hyperbolic square, and go for the supersymmetry treatment. In most of the cases, the partner will turn out to be. If you work the other way around, it may not be that easy. But if you start with this one, make some changes here, then of course you can work out the real partner, and how it is different from the typical solitonic sec hyperbolic square.
Okay. Yeah. So have you analyzed the position-dependent mass potentials?
Yes, that has also become another game. Yes, we have analyzed that, but then the problem is what mass function should I take? Now, this mass function is it can be sort of adjusted so as to have some interesting results. But what Titika Dubey did, that was very interesting. That she took the Leonard thing and then went over to a system which then spoke of the momentum dependent first. I think they are the first ones to write down the entire Hamiltonian for the momentum dependent mass, and that I found very interesting. That is a new direction. Of course, there is no doubt about it.
Thank you, sir.
And have you considered the PT symmetric version of Matthews-Lakshmanan oscillator?
PT symmetry of plus minus?
PT symmetric version of Matthews-Lakshmanan oscillators, non-polynomial oscillators. Probably.
Your answer to your question is yes as well as no. We did not really focus on Matthews-Lakshmanan oscillator, but I believe it might work. I'm not too sure. But we did work on non-polynomial oscillator and worked out PT symmetry for that. I have a paper with Madam Kane, and that paper was published in PLA or something. We went for non-polynomial oscillator. But then the problem is that with respect to non-polynomial operator, there is inherent singularity in the denominator. I mean, the denominator runs to 0 for some values, and I left the problem at that. But specifically, I did not try Matthews-Lakshmanan oscillator. But what I did, I tried these position-dependent mass systems for Matthews-Lakshmanan oscillator, and those papers have been published in Journal of Physics.
Okay. Okay, then. If there are no more questions, let us thank Professor Bagchi for a very interesting presentation of PT symmetric potentials. So thank you very much, Professor Bagchi.
Thank you. Thank you also for your kind attention, especially for having invited me here to present my results. And this is a good opportunity to show you some of the interesting results of PT symmetry which are with us now.
Okay. Thank you very much.
Thank you.
Thank you. Bye. Goodbye.
Bye.